So this is a starting of the class. Last time it was an introduction, an overview of the class. So now we start really with chapter 1 about ordinary generating function. So I start with a simple example, simple binary tree. So here is a picture of a binary tree. And we define a binary tree as a triple with a left subtree, a right subtree, and the root. The root is this vertex. The left subtree is this one on the left, and the right subtree is this one. And left subtree and right subtree are again binary tree. So it's a recursive definition, which are very common in computer science. And to stop the recursion, then it may be a triple with a root, or maybe it will be reduced to a single vertex, which is called a leaf, or an external vertex. So it's in the binary tree, there is internal vertex, a vertex with a left subtree and a right subtree. The root of the left subtree is called the left son. The root of the right subtree is called the right son of this vertex. And external vertex, it's when you stop, there is no left tree, no right subtree, no son. So this is the image of a binary tree. And we want to count how many such binary tree with n internal vertices. It's very elementary lemma that if there is n internal vertices, there is n plus 1 external vertices. Here there is 7 internal vertices and 8 leaf or external vertices. So very elementary combinatorial problem. How many such binary tree with n internal vertices? So from the definition, from the recursive definition of the binary tree, you get a recurrence relation between the number of binary tree with n plus 1 internal vertices and this summation, where Ci is a choice of a left binary tree, subtree, with I vertices. Cj is a choice of the right subtree with j vertices. Total number of vertices in both left subtree and right subtree is n, because n plus 1. The shift is 1 because of the root of the binary tree. So you choose any left subtree with I vertices, any right subtree with j vertices. Total number of vertices is I plus j plus 1. And the choice of the left subtree and right subtree are totally independent. There is no relation between the left and right subtree, so you get easily this recurrence relation. To start the recurrence, then you have the number of binary tree with no internal vertices, just reduced to a point, to a leaf, it's 1. So you can play with this recurrence relation and you get all the numbers, 1, 1, 2, 5, 14, 42. For example, C6, 132 is deduced from this recurrence relation. So you have to try to get a nice formula for Cn. How to solve this recurrence relation? I give you immediately the answer is Cn equal 2n chosen divided by n plus 1. So it's a very nice, simple formula. The biggest of the binomial coefficient in the Pascal triangle, let's go back much earlier, China, India was 1,000 years ago. The biggest binomial coefficient in the Pascal triangle is divisible by n plus 1, and the ratio is a Catalan number. And factorial is 1 by 2 by n. So you have this very simple formula, and maybe you can check that this formula satisfies the recurrence relation. or maybe you can find some other technique to solve this recurrence relation, but this maybe it's very classical in enumerative combinatorics. It's starting from recurrence relation and trying to solve this recurrence. This is maybe the old time when there was recurrence relation. Now there is very few, no more recurrence relation. So it's classical, I mean, you see this number Cn, here it's another notation, are in fact, they are named Catalan numbers from Eugène Catalan. Eugène Catalan, see the 19th century, and you see this paper in 1838, and you see this is the recurrence relation giving this Catalan number, and even he gets some formula, etc., etc., 1, 2, 5. This is the biggest binomial coefficient. So this is classical. In fact, this number called the Catalan number, they go back much earlier than Catalan. In fact, it goes back to Euler. Euler introduced this number in 1751. Of course, he was not counting binary tree. Also, Catalan was not counting binary tree. They were counting something different, which is called a triangulation of a convex polygon. And what is a triangulation of a convex polygon? Or you take any convex or even a regular polygon and you put some diagonal in blue, such as that two diagonals never intersect, except they can touch at the ending point, but they don't intersect inside the polygon. And you put as much as you can blue diagonal. You put 1, 2, 3, so when you put the maximum possible diagonal, you get a triangulation of the polygon. The interior of the polygon is subdivided into a certain triangle. And the number of such triangulation is again the Catalan number. So in the next chapter, in another chapter on the bijection related to Catalan number, I will show you a nice bijection between triangulation and binary tree. Maybe you can start as homework to find this bijection. It's a classical bijection which relates this triangulation to a binary tree. So here is a letter of Euler. He has a good friend, Goldbach, in Moscow. Euler was in Berlin, and Goldbach was in Moscow, and he sent letters. They were exchanging on number theory. But amazingly, at the end of this letter on number theory, then suddenly he was interested, Euler, in counting. Here are the 5, see in this notation, the 5 triangulation of this regular polygon with 5 vertex. And then here is a Catalan number. 1, 2, where they are? 1, 2, 5, 14, 42. So here is a Catalan number. And even he has the formula. He gets the explicit formula. This is in this notation 1 over n plus 1, the binomial coefficient 2n choose n. And even he gets what we are going to introduce in this lecture, the generating function for Catalan number. So it's a formal power series. And even he gets the explicit expression for this generating function. So he was really a pioneer in combinatorics. He introduced formal power series. After, in the following, Gauss says this is nonsense because there is no convergence. The radius of convergence of this formal power series is 0. So there is nonsense. But this makes sense. We will see at the end of the lecture that all this, if you take this formally, all this makes sense. So Euler was really a great mathematician, a great savant, and a great combinatorist. And even he was introduced the singularity of the generating function. So this is analytic combinatorics, when you relate the asymptotic of the AN with the singularity of the generating function. And this was in 4 September 1751. So an intuitive introduction to formal power series and ordinary generating function. So let's go back to this Catalan number. 1, 2, 5, 14, 42, etc. You can make with them a polynomial. where you spread the variable t, t2, t3, t4, and even if you go with no limit in this monomial, you get a formal power series. So this is just intuitive introduction to this. So the coefficient of t power n will be exactly the Catalan number, Cn. And we denote this generating function of formal power series, or we call this a generating function for the number an. It can be considered as a function, even if there is nonsense, no radius or convergent, but it's, everything is formal in this lecture. And we will let's play with some formal power series without defining explicitly what is the formal power series. Let's just play intuitively. So the inverse of 1 minus t is equal to this. Just take this, multiply by 1 minus t. So you have this, minus t times all this, and you get exactly 1. Now, a little exercise. What is 1 over 1 minus t plus t2? So I claim that this is an expansion of this rational fraction into formal power series. And the green number, 1, 2, 3, 5, 8, 13, 21, you recognize classical numbers. Now, after Catalan number, we have the Fibonacci numbers. So in fact, this is a generating function for Fibonacci numbers. And let's play with this calculus. So the inverse, 1 over 1 minus u, this is u, is 1 plus u plus u2 plus u3 plus u4, and you have to replace u by t plus t2. So this is 1 plus u to the square, plus u to the cube, etc. So and you put in each column, you put all the coefficient, all the monomial appearing with the same degree. So this is the term in t2, in t3, t4, t5, and if you sum in each column, you get 1, 2, 3, 5, 8. You get the Fibonacci numbers. So let's, as an exercise, to check that using this expansion with binomial coefficient, you get exactly the Fibonacci numbers. So this is an example of calculus with the formal power series. You can do this calculus. In each column there is a finite number of terms in each column, and you get explicitly an infinite power series. So can we do this? This is nonsense. Formal power series, you can do everything you want, but there is some, you're not completely free to do this. T plus t plus t, there is nonsense of this, or 1 plus 1 plus 1 plus 1. There must be something, there is an ultrametric topology on this formal power series. So sometimes it's not completely free. There is some forbidden things to do. So let's make a real definition, the formalization of this formal power series. So I will take formal power series. It will be an algebra, and it will be in one variable. So the coefficient will be in a certain ring, a commutative ring, k. Usually k will be the integer or the rational number, complex number. Here k was just a Catalan number, it was just an integer. But sometimes in more complicated example, the ring of coefficient will be polynomial in integer with variable alpha, beta, gamma, which will count the parameter of the enumerative problem there. For example, if you want to count binary tree by the number of left edges going after a leaf, then you will have an extra variable, and this extra variable, you can put it in the coefficient of the power series. So this is the algebra of polynomial with coefficient in z and formal variable alpha, beta, etc. So this is a polynomial. Everybody knows a polynomial algebra. Polynomial with multiplication, sum, multiplied by a scalar, and formal power series. It just this is a notation. It will be rigorously defined next, but this is a notation for this infinite sequence. So for the moment, a formal power series is just an infinite sequence of coefficient, a0, a1, a2, an, all these coefficients are in the ring K. And for the moment, this is a notation as a polynomial plus point. So this is a formal power series in one variable t with coefficient in the ring of K. And it's an algebra, so I define three operations on the formal power series. There is a sum, the product, and the product by a scalar. So the sum of two formal power series is defined like this: H equals F plus G. So if F is sigma of an t power n, if the coefficient of t power n, the nth term is an, for G is bn, then the term coefficient of H will be Cn equals the sum of the coefficient. Very easy and natural. Now the product of two formal power series is just an extension of the product of polynomial. So if the coefficient Cn of the product will be the sum of the product AP BQ, AP and BQ for F and G, for all P and Q, such that P plus Q equal N. It's well defined, and it's just an extension of the product of polynomial. Then you can define the product by a scalar. If I take a coefficient of the ring lambda times F equal just defined by this very natural Cn will be lambda times An. So we have a vector space with these two, and then with this give you an algebra. It's an algebra formal power series, an extension of the algebra of polynomial in one variable. Okay. So we'll call, if you have a sequence of coefficient, of numbers, of coefficient in the ring K, then we will call sigma, the power series, sigma an tn, the generating function of the coefficient. We'll call this ordinary generating function when you put the power series like this. And in another chapter of this course, I will introduce exponential generating function. Sometimes it's much more useful to introduce this. It's the same, but instead of putting an, I put an divided by n factorial. So some problem in combinatorics fit very well in this setting, and some problem fit very well here. The typical example is Catalan number. All the Catalan garden we are here, and for the n factorial, for permutation, or we have seen Hermite polynomial, we have seen the many other structure with exponential structure which fit very well with this generating function. Now if you have a family, suppose we have a family of power series, indexed by a certain index I, you have many power series, indexed by the I, belongs to this set capital I. I will say that definition, this family is summable. I mean, I can define this rigorously. If and only if we have this condition. So this condition is for every n, take the set of indices I belonging to capital I, such that the coefficient of t power n in the power series fi of t is non-zero. And then the condition says that this set of integer is going to be a finite set. So this means that in this big summation, there is only a finite number of indices, a finite number of fi, which contribute to give you the coefficient t power n. And the coefficient of t power n will be the sum of all these coefficients of this finite subset of power series. So this makes sense to define this. This was an example, the intuitive introduction to formal power series. This family of t plus t2 power I, this is fi, they are summable because if I take the coefficient of t power n, in each column, there is a finite number of terms contributing to t power n, and this for any n. And this finite number of terms define you the sum of all this, the coefficient of t power n is the sum of all the coefficients in the same column. Another example, now this notation makes sense. At the beginning, I introduced this as a notation for this infinite sequence, but now this is rigorously defined because the family an Tn is summable, and the sum is exactly this power series. Each fi is reduced to a single term, the term ai t power I. Analogously, we can define infinite product. It's analog definition. If you take the contribution, if you try to get the term of t power n, then t power n will be the sum of some product of some term involving this power series. And if all the terms which give you t power n are finite, then this makes sense, and I can define this infinite product. So it's very analogously to a summable family. This is possible if for any n, the coefficient of t power n is going to be the sum of product or sum of this gi, and I suppose that all the indices of I contributing to t power n is finite and give you the coefficient of t power n. So a typical example is this one. Take 1 over minus qi, which is 1 plus qi plus q power 2i plus q power 3i. This is a family of products. This is well defined. And we will see that this is a generating function for partition of integers. So this is typically an infinite product, which is very well defined in the algebra of power series. So we'll work also with other operations. There is other operations, they're analogous in classical analysis. If you take a substitution, you have a 2 power series, and you make a substitution, but to make sense, you must have the constant term of g of t is 0. So you take this family of power series, an multiplied by g of t power n is going to be summable, and so this makes sense to have the summation of an g power n, g of t power n, and this is exactly what we define the substitution of one power series into another power series. And this corresponds exactly to a substitution of function in real analysis. If your formal power series makes sense, I mean there is a radius of convergence, which is non-zero. If it's really a function in analysis, then this corresponds to the substitution of a function into another one. So we will see some example with binary tree, and what a nice example is what is called the Strahler number in a binary tree, and to explicitly give the generating function, we need substitution inside the binary tree. There is the inverse also. The inverse makes sense also if this means also the constant term is 0. The order of a power series is a minimum term of non-zero, the minimum degree of a term non-zero. So this power series begin with at least at most power t. The constant term is 0, and I can define this as the inverse of a formal power series. Another operation is a derivative of a power series. Derivative is just f prime or df substituted, so you just derivative each term by term. So you have an t power n, so it means n times t power n minus 1. Yes?
Would you mind going to the previous slide? There is a silly question.
Yeah.
You wrote down V0 equals 0.
Yes.
So is it easy to see that is forced by wanting the definition to make sense?
B0, this is sorry, I don't understand. I suppose be 0 by 0, which means the order of G is bigger or equal to 1. The order of a power series is the minimum, the degree of the term, the minimum degree of a term with the non-zero coefficient.
I understand the condition.
But if you don't have this, then you will have problem to define the power series.
One, so one will be from 0.
Each term will be infinite.
Because if you have a constant here, then there will be an infinite. You are summing infinitely some constant, and this is not allowed with formal power series, like 1 plus 1 plus 1 plus 1 plus 1, or t plus t plus t plus t plus t infinitely. Then this does not make sense. Inverse derivative. So you have also exponential and logarithm. This is a classical expansion in analysis of exponential and logarithm. But so you can substitute t by f, and you can define the exponential of a power series. Take the logarithm of a power series to the condition that, again, the constant term of f is 0. If there is no constant term, then you can define, substitute f here. It will be sigma of f power n and factorial, or you can define the logarithm of 1 plus f to be sigma of f power n over n. And you can define also 1 plus f power alpha. Alpha is any rational numbers, or any integer or rational number. So if it is an integer, you get the binomial coefficient, but you can take any numbers, and 1 plus t power alpha will be this. And this gives you this formula, and you can substitute t by f. So define the binomial power expansion of 1 plus f. And then it will be possible to extend all this definition to formal power series with several variables. So it's again an algebra, and so all these operations I defined before are well defined. It's an extension. I'm not going to repeat everything. And some new operation appear, the partial derivative to a certain variable, which I did not have at the beginning, with only one variable. And then also it will be convenient in this class to use formal power series in several variables which are not commuting. In computer science, I am embedded in the computer science laboratory, and we have the language theory, we have the word, we have a non-commutative power series, and the non-commutation fit very well with the quantum combinatorics. So I will use classical notation for non-commutative variables. So the free monoid. What is a free monoid, which we denote usually x star? So x is an alphabet. It can be A, B, C, or 1, 2, 3, 4, 5. It's the elements of the alphabet are called letters. And a word is just it's written like this. It's just a sequence of letters. And we call this a free monoid generated by x. Free monoid, there is a product which is associative, and there is a neutral element. And it's weaker than a group. There is no inverse in general, but there is only two conditions. So what is the product in this set of words? The product of two words is just a concatenation of the two words. You take the word you and multiply by the word v. And in this product, there is a neutral element. Neutral element denoted by E, it's just the empty word, no letters. The length of the empty word is 0. So the length of any word, the length of a word is it's a total number of letters inside the word. Or it can be also seen as the sum over all letters. This notation is the number of occurrence of the letter X inside the word you. How many times each letter appears in the word you? If you sum over all possible letters, you get the total number of letters in the word you. So very easy, all this notation. But sometimes I will use them in the class to see some time pass or to see things as a word. And some easy notation is if you have a word, you cut a word in two parts, u, then you have a left factor u and v, the right factor, and general factor, when it is inside the word, it's a portion of the word where all the letters are consecutive. This is a factor. A factorization of a word is just you split the word in a product of u1, u2, uk, where each of the ui are words. So don't confuse factor and subword. A subword is something like this. When you extract from the word, you take some letters and you put them together to get a subword. So subword is a portion of the word. It's not necessarily consecutive letters. A factor, all the letters are consecutive. And subword or subsequent subword, it's not necessarily, you extract not necessarily consecutive letters. And in computer science, any subset of a free monoid is called a language. So there is a language theory. You can take the sum, the union, the product of language. And then sometime I will use the algebra of formal power series in non-commutative variable. It's a formal, there is the algebra of polynomial in non-commutative variable and the algebra of formal power series in non-commutative variable. It's just a sum, formal sum over all word. And for each word, you take a coefficient C, W included in K. So I will not make more comment on this. You can define the sum, the product, as usual for the commutative case. And sometimes it's useful to work with this non-commutative power series, non-commutative algebra of polynomial. So now I am going to define some operation on the level of commutative object. So this operation, it will be the sum, the product, derivative, all this will reflect the operation on the word of formal power series or the word of classical analysis. So I will give again an intuitive introduction to this operation on, I will come back with my binary tree. So a binary tree is a triple, a left subtree, the root, and the right subtree. I want to count the Catalan number, how many such binary trees with n internal vertices. So we have seen the recurrence relation in classical combinatorics. Now we have introduced formal power series. So this recurrence relation, now you can see is equivalent to this algebraic equation. And taking the square of this formal power series, if you take y is the sum of the generating function of Catalan number, if you take the square of this, it's equivalent to do this. Now the shift between n and n plus 1 is exactly the t. And this means it's a binary tree with a root and a left subtree and right subtree. And this is a special case where the tree is reduced to a single vertex, an external vertex. So this recurrence relation with this condition is equivalent to this algebraic equation. But now we can avoid the recurrence relation, go straight from the definition of the binary tree straight to the algebraic equation of the generating function. So in the modern time now you can write a binary tree is equal to this. We reduce plus this picture, the root and the left subtree and right subtree, which I can write this way. So now it will make sense. I will formalize this precisely, that this family of objects is the sum. Here I have the sum at the level of combinatorial object. It can be reduced to a single leaf, or it can be the triple, and this is a product of combinatorial object. I have the sum of combinatorial objects, the product, and I will make sense, I will define properly what is the sum and the product at the level of combinatorial object. Now, if you have this equation at the level of the combinatorial object, then you can project this equation into replace b by y, replace the unique leaf by 1 and replace the root. I am enumerating binary tree according the number of internal vertex. The root is an internal vertex, it gets t. This is an external vertex, there is 1. And this is a product, this product of three things, the roots b and b give you ty to the square. So once you will get the formal definition of product, sum, and operation on combinatorial object, you will immediately go from the definition of binary tree to go to this equation without making any recurrence relation. So now you can, this equation, if you want really to get the Catalan number, so here is a proof of the formula I give for the Catalan number. You can solve this as any quadratic equation. So y is going to be this. Right? This is in elementary school. Consider this is real numbers. It's an equation of degree 2. There is a formula. It's -1 plus or minus square root of this. You have to choose there is plus or minus in the resolution. But if you put plus, it will not be a formal power series. If you put plus, there will be a term in 1 over t. So you have to put minus. And now 1 minus 40 to the square root. And now you just apply the binomial coefficient. Expansion, apply expansion 1 plus u power m. With m is 1 over 2, and u is minus 40. Here, 1 plus u power alpha. Alpha is 1 over 2, power m, and u. So you just expand this. So now it's going to be an infinite power series because its m is 1 over 2. If it was an integer, it will be a polynomial. It stops. This is the expansion of in the binomial triangle. But m equal 1 over 2. You have an infinite power series. And then if you replace m by 1 over 2, if you replace u by minus 4 power t, then you get the formula for the Catalan number. So this is one way to prove the number of a binary tree is exactly given by this formula. So now I give a formalization of this operation on combinatorial object. Sometimes it's called symbolic calculus. Symbolic calculus, a symbolic method with no recurrence relation, just by symbolic calculus on the set of combinatorial objects. So I follow there is a book of Philippe Flageolet on analytic combinatorics, and the first 120 pages is about enumerative combinatorics, and this symbolic method explains this. So symbolic method works for ordinary generating function and also for exponential generating function. So for ordinary generating function, I follow the philosophy of the book of Flageolet, but for exponential generating function, I will follow another method called the spaces by the people in Quebec, in Montreal, by Joyal theory. This is fit better for exponential generating function. Yes, Sundar?
Book of whom? What is the author's name again? The book of whom?
Here, so here is the book by Philippe Flageolet. He is a combinatorist. Unfortunately, he died a few years ago, and this is Analytic Combinatorics in Cambridge Mete Press. It's a big book, it's 800 or 900 pages, and the first 150 pages is about enumeration combinatorics, and he called this method the symbolic method to work at the level of combinatorial object with operations, sum, product, derivative, integral, everything, and then you project this word to the word of generating of a formal power series. So analytic combinatorics means instead of enumerating exactly, for example, Catalan number, what is the number of binary tree, if you don't succeed to find explicit formula, at least you hope to have asymptotic formula, that an is going more or less to be equivalent, for example, for Catalan number, it's 4 power n multiplied by n power minus 3 over 2. It's multiplied by something more. So, and analytic combinatorics, it relies mainly on to have the analysis, asymptotic analysis of an is related to the analysis of near the singularity, the main singularity of the power series, of the generating function. So it's a study of so you have a lot of analytic calculus with analytic function and holomorph function, all these singularities. So, but in this class, only exact formula, A equal B. Not A is more or less B, but here I like equality, I like bijection. If there is not exactly equal, I cannot find any bijection. It's up to one, so yeah. But it's another philosophy. I don't feel comfortable in analytic rhetorics, but well, look the book. It's 900 pages, and it's related also to probability and analysis of algorithm, physics, etc. Okay, so formalization of what I have done with binary tree. So let's define what is a combinatorial object. Usually, intuitively, it's something you give to a kid, draw me a binary tree, draw me a permutation. Any kid should be able to find an example of the combinatorial object. If you say to a kid, draw me a finite simple group, he will not be able to do it, so this is not combinatorics. Combinatorial object, something you can really, you understand definition, you can give immediately some example without any complication. So, but let's define it formally. So I will define this way. So I will define a class of valued combinatorial object. It's a class A round. It's a pair. A is a finite or a numeral set. So for example, A can be the set of binary tree or the set of permutation. And there is a weight V. V, evaluation of a weight, is any function going from A to a set of polynomial, maybe in several variables, and with coefficient in a ring K. So you have you have a set of objects, enumerable, plus a certain weight, such that you have the following condition to be able to define the generating function of this combinatorial object. So the condition star is the following. For any W, which is a monomial in the polynomial K of X, take any monomial and define A index W is a set of elements of A which contribute to the monomial W. So it's a set of alpha such that the coefficient of W in V of alpha is non-zero. So we take all the elements which contribute as they weight to give some contribution to W. And then the condition that for every monomial W, this set is finite. So this is the condition. And with this condition, then this family of power series is summable, and I can define the generating function of such object. So the generating power series for a certain family of object A rond, it's F index A rond. It's the sum over all elements of capital A, V of alpha. And this makes sense because for each, this is a sum of monomial in the ring of polynomial in variable X and coefficient K. For each W, there is a finite number of objects contributing to W. A finite number of alpha will give contribution to W. W is any monomial in this ring of polynomial, and this makes the family B is summable in that sense I gave before, and this gives me this definition. So this is a formal abstract definition of a combinatorial object. maybe you don't recognize, but this is, at least I have to make something formal. It's maybe a little boring to do something formal, but you have to, this is a course, I have to settle some foundation on in this combinatorics. So examples, if the variable, the x, there is only a single variable t, so the weight of alpha will be t power n, and then, so I will call n will be the size of alpha, and an, by the condition star, there is a finite number A index W, W is t power n, so this set is finite. There is a finite number of elements such that V alpha equal t power n. This is a condition star when I reduce the weight to be just a t power something. So I have this generating function where an, I can say that an is the number of elements in capital A with a size equal to n. Even if there is no size at all, there is no number of points, there is just an abstract definition of the weight. And more generally, I can define also this. I have a single variable t plus some other variable, extra variable y. So the weight of the object will be a certain weight, w, multiplied by t power n. And in general, I will put a0 equal 1. There is only one empty object. So you will get again some, you are going to enumerate, the generating function will be enumeration of all the objects of size n, and there will be an extra weight, which can be some parameter, because we will enumerate some object of size n with many, many other parameters. This is very important in different fields. Okay, so I just repeat what I have done. I have an abstract definition of a class of valued object with this fundamental condition star, which make me a formal definition of the formal genetic power series of the object. And I have these two example objects of size n. So now I can define some operation on this class of combinatorial object. So the first operation is the sum. So you have two classes of objects, the class in blue with this weight, the class in red with this weight, and the sum is going to be the following. So I have to define a new valuation and a new set of objects, C. So C is a union of A and B with the condition that A and B does not intersect. They are disjoint union. And then the weight of the object on this union is the restriction. When I am in A, I take the weight VA, and then when I am in B, I take the weight VB. So obviously, the generating function for the sum of the two classes is the sum of the generating function. The definition is made so that it reflects the operation on the formal power series on generating function. So sum is you have to have a disjoint union of the object. Now the product of two classes. So the set C of the product is just the Cartesian product of A and B. And the weight, so an element of C will be a pair alpha beta with alpha in A and beta in B. And now the weight of an element of C is just the product of the weight of each component alpha and component beta. Example, if I take the size, when I talk the size, the weight is only t power n, so the size of the product will be the sum of the size. Example of binary tree. The binary tree was, if it's not reduced to a single point, it was a triple, it was a product of the root multiplied by two binary tree. So this is now a rigorous definition of the product of two binary tree. And of course, this is made so that the generating function of the product is a product of the generating function. If you take the product of these two functions, because of this definition, of this definition, you get easily this lemma that the product of objects reflects the product of the generating function. So another operation is sequence of something. Suppose I have a combinatorial object A. I can define sequence of object of the type A. Sequence is, this would be the empty object, empty class, plus the class itself, plus the square of the class, plus an, plus etc. So sequence, you take, for example, sequence of binary tree, you take one binary tree, a second binary, a third binary, you take a sequence of such binary tree. Instead of taking only two, I can take any numbers of binary tree, and then you can easily show that the generating function for the sequence of object of type of this type is going to be 1 over 1 minus this one, because it's 1 plus f index A plus f to the square plus f3 plus f4, etc. So we will see before the end of this class some example with partition and Ferrer diagram. So all this, in flageolet book, there is more operation, but I don't want to make too complicated. This is the main. The main is sum, product, sequence, and we will show also, I will show you next time, the substitution of an object into another one, and this can solve some difficult problem in combinatorics. So let's do example of this lemma and operation on a combinatorial object. So let's do example with partition. So partition is the partition of set into subset, but here it's partition of an integer into a sum of integers. The partition of an integer, I take n equal 43, for example. A partition is just a decomposition of the integer into a sum of non-zero integer, and I put them in decreasing order, because in a partition, in the decomposition, the order has no importance. So this is a classical subject also, introduced by, again, Leonard Euler. He gave some generating function for partition of an integer n. And such decomposition, you can visualize it as a Ferrer, what we call a Ferrer diagram. So you put the part of the partition from decreasing from bottom to top, and each part you draw a row with the number of cells is exactly the number, is exactly the part. So there's 6 cells, 5 cells, and you put each row left justify here. So you get this kind of picture. Ferrer diagram is a visualization of the decomposition of n into a sum of integer. N is the total number of cells of the diagram. And each part, this is called the part of the partition, are the number of cells in each row of the diagram. In physics, it's called Young diagram. So 43 cells in this Ferrer diagram. Another example, if you prefer to put point instead of cell or square, this is another example. And we are interested to find the generating function for the number of partitions of the integer n. So here there is 2 partitions. Here for 3, there is 3 partitions. 4, 5, you see, there is number is 1, 2, 3, 5, 7. Here this is a partition reduced to only 1 part. Here with 2 parts, 3 parts, 4 parts, and 5 parts. So I get a generating function, and usually in partition we put some, instead of putting t variable, you put q. You will slowly understand why is q instead of t. So q is for q series, q calculus, and the magic of q is, this was in all time using q. The magic is that there is now a connection between combinatorics and quantum mechanics. And the Q of combinatorics is beginning the same as the Q of quantum, so the world is very well done. Its notation are well done. You have sometimes we call quantic combinatorics in this idea. So I want to find an explicit expression for the generating function of integer partition. An is the total number of partitions of n, and I claim that I'm going to obtain this generating function by applying the lemma sum product sequence of the previous section about operation, direct operation on combinatorial object, no recurrence relation, nothing. You look the combinatorial object and you deduce as a combination of something simpler made by substitution, sum, product, everything. In the same way, I was decomposing a binary tree in smaller binary tree, but this decomposition is obvious. It's come from the definition. Now it's a little less obvious with partition. So let's start with q power I. Q power I, it's a row with I cell. It's a partition of the integer I with the part, only one part, which is I. So its coefficient is 1. This is q power I. Q power, if you want, it's the weight of a row, single row with I cell. Each red dot is weighted q. Total weight is q power I. Now if you take repeat a sequence of row like this, 1 row, 2 rows, 3 rows. So take a rectangle. This is going to be a rectangle with I column. So such generating function of rectangle having I column, it is a sequence of row. 1 row is q power I. So sequence of is 1 over 1 minus generating function. So just apply the lemma on sequence of object. I have one object is this. Sequence of this is 1 over 1 minus qi, and sequence of this is exactly a rectangle with only I column. The height of the rectangle can be anything. Now take a Ferrer diagram like this. Ferrer diagram can be decomposed into a rectangle. Here it's a rectangle with 1, 2, 3, 4, 5, 6, 7, 8. I equal 8. Now this is 5, this is 3. So you have a decomposition. This is make me slide. In the old time we were doing with overhead projector, I take this and I have a decomposition into slides. So I try to do the same with the modern technique. And what maybe you can see it, here there is some slides which are empty. So there is rectangle with 8, but there is no rectangle with 7 columns, no rectangle with 6, one rectangle with 5. So you have a decomposition into rectangle, maybe empty slides. And so you get this formula. 1 over minus q, this is rectangle with 1 column, rectangle with 2 columns, maybe empty, it starts with 1, with 3 columns, etc. Rectangle with m column. So what you get, this is a generating function of Ferrer diagram. The m Ferrer diagram such that the number of columns is at most is bounded by m. So it's partition such that the part of the partition are bounded by m. I get this finite product. Now if I take the limit, if I don't put any bound on the biggest part of the partition, no bound on the number of columns of the rectangle, I get this infinite product. Take the limit when m go to infinity, so you take off the bound you have in the number of columns. So this is a proof of the nice proof. Maybe I like it. It's because you look your object and you make a decomposition. The Ferrer diagram is decomposed into rectangle. Rectangle is sequence of row, and you apply the lemma of a product substitution. No substitution, sequence of, and you get this generating function plus a limit case. So this is a typical example now of course, if you do by brute force, try to find the coefficient of n. This is in college school. Find the coefficient of n. You will see that n is a number of ways to decompose n into coins with 1, 2, 3, 4, 5. You will get the number of partitions directly. But maybe this is more elegant now to work with with this lemma. Allez, a few exercises. So instead of taking this, the whole infinite product, which is the generating function for all partition, you limit this infinite product to all the indices I, which belong to a certain fixed subset, capital I. Fix this subset, finite or infinite, and you take this infinite product. So this exercise shows that the coefficient of q power n is the number, this coefficient, which depends of the set I, is the number of partition of n, such having the condition that the part of the partition, all the part belong to the subset capital I. Easy exercise. Now, less easy exercise. Second exercise, I introduce the notion of D partition. D for difference. It's a special case of partition. It's partition lambda with part lambda 1, lambda 2, lambda k, such that if you take two consecutive parts, they differ at least by 2. So it's partition in distinct parts. There is no repetition in the part, but there is more than distinct part. If you take two consecutive parts, the difference between the two must be bigger than 2. And the exercise is to show that the generating function for D partition is given by this summation, just infinite sum for all m strict positive or 0, q power m to the square, and divided by 1 minus q, 1 minus q2, 1 minus qm. And I give you a hint for the exercise. The hint is in French. I forget to delete. Find a bijection. There is a bijection between D partition having exactly n parts and partition with at most n part. And such as that, you see there is a shift. The q power, the number of cells is going to increase. There is a bijection with partition with at most n part, and D partition with exactly n part. And there is an extra weight, q power something 1 plus 3 plus etc., which will give you this coefficient. There is a shift in the bijection. I don't say more, but I'll try to prove this exercise. And this, I will not going to prove this famous identity, but this is related, D partition are related to the famous Roger-Ramanujan identities, the famous Indian mythic mathematician. Here his home is in not far from here in Tamil Nadu, in Kumbakonam. Well, you have to go there too. There is the historical ambience of Ramanujan, and here are the two famous Ramanujan identities. So see the left-hand side is exactly, see, I put this here, it's a generating function for D partition. Left-hand side. And the right-hand side, with exercise number 1, it will be all partition such that the part are equal to 1 and 4 modulo 5. So it can be 1, 4, 6, 9, etc. Let's give an example of this first identity. So let's take the coefficient of q power 9 in both sides. Q power 9, so it will be the number of D partition of 9. Here there is 5 D partition. 9, 8 plus 1, 7 plus 2, 6 plus 3, 5 plus 3 plus 1. So you see it's partition such that the difference between two consecutive parts is bigger or equal to 2. Here the difference is exactly 2. Here the difference is 7. So there is only 5 such a D partition. And the right-hand side tell you that the coefficient of q power 9 is also the number of partitions of 9 such that the parts are equal to 1 and 4 modulo 5. So it can be 1, 4, 6, and 9. And I have exactly 5 such partitions. 9, 4 plus 4 plus 1, 6 plus 1. So the part is 1, 4, 6, or 9, and there is 5. So this is a miraculous formula. This is one of the jewels of combinatorics. This is true for any n. If you take n equal 100, you take for any n, there is same number in both sides. If you find a nice bijection to prove this, you will be famous. There is some bijection, but not...
You don't like it.
or almost bijective proof. It's even an open problem. Is there a nice, what means nice bijection? And is there a definition of a nice bijection? And is there a nice bijection for this identity? So, well, in 1980, Garcia-Milne find a bijection, but it's terrible bijection. Now the second Roger-Ramanujan identity, the left-hand side, you just shift n2 in n2 plus n. You just add this, and the right-hand side, now it changed completely. Now it's partition in part equal to 2 and 3 modulo 5. So what does this mean to shift this by n? It's exactly departition with part not equal to 1. See, here I have 5 partitions. When I shifting this by n, means you delete, you eliminate all the departition having part equal to 1. So instead of 5 partitions, I have only 3 partitions now. In the right-hand side, now it's changed completely. Take all the partitions with part equal 2 and 3 modulo 5. So you can have 2, 3, 7. And the partition of 9 with this kind of part is only 3. So this is the second Ramanujan identity. And why is it called Roger-Ramanujan identity? Because Ramanujan conjectured this identity. In fact, he did not prove when he was in Great Britain at the invitation he was during the First War. He was in Great Britain and he conjectured this, and he found in fact a book by Rogers. There was a paper in a long time ago where this identity were proved. And now during the war, also Schur gave another proof, but there was no contact. It was the first World War in the world. And then Baxter was the third man to prove the identity. Baxter is a physicist, and he solves the hard hexagonal model. He needs this identity. He discovers them by experiment, and he proves them. So there was 3 people who proved them without knowing. But the name Ramanujan is so famous that they are called. What time is 3:09? Okay, so I will now introduce the philosophy of bijective proof, bijective proof of an identity. So you know, it's like at the Greek time, it was many proofs were visual. 2,000 years ago, this is a visual proof of this identity. N to the square, you just look the color equal 1 plus 3 plus 5 plus 7. So this is called visual proof. Or sometimes it's called proof without the word. You don't have to say anything. You just look the picture and you get a proof of this. So this many proofs in the Greek time were done like the visual proof, like the Pythagoras theorem. Pythagoras, you see, you know, Pythagoras theorem. You take a rectangle. Let's give the proof without words. Just look what I am doing. See, in the movement, the area of the yellow part keep invariant. this is A, this is B, and this is hypothesis C. So this is kind of proves the Greek love much. There is many people in secondary school also do such kind of proof, but nobody maybe believe it's new that some deep identity can be also proved using this kind of thing. Many people think that only easy identity can be done in a visual way, but the philosophy of modern combinatorics is to go much deeper in such proof. So I will prove this identity in a visual way, by just applying what we know. So here is a beautiful identity. You see, if I was not putting the two, this would be Ramanujan identity. If you put a square, then it's again give you a classical generating function. So let's prove this in a visual way. But what we know from this class. So the right-hand side, this, is we know now from the class that this is a generating function for a Ferrer diagram, for partition of an integer. Now the left-hand side. So there is three terms, in green, a red, and a blue term. So q power m to the square, it's a square m by m. Now the red term. This we have seen, it's a Ferrer diagram with at most m row. And I take the square. So again, another Ferrer diagram in blue with at most m row. So now I put these three diagrams together, and so this red, I can put it, glue him to the green one. There is at most m row. The square is m by m. So this blue one, I take a symmetry, the diagonal. So now it became a diagram with at most m column, and I can put it on the top of the square. This is the left-hand side. This is the right-hand side. And what is the proof of the identity? The identity means that if from a Ferrer diagram you extract the biggest square you can find in the Ferrer diagram, like this, what you get, what remains, here is a Ferrer diagram with at most m row, here a Ferrer diagram with at most m column, and that's the proof of the identity. End of the proof, you see. So this is the spirit of this class. It's to try to make, between the calculus and the bijection, to make an interplay, to make a dialogue between the two, to play with the calculus, to play, as in the first lecture I gave with the Meller identity for Hermite polynomial. There was some part of the identity which became some blue point, red, etc. So, and then you play with the picture, and then you go back to the identity. So this was the philosophy of the, like drawing here, same philosophy. Drawing calculus, I replace some part of the calculus by blue, red, or green picture, and I compute the drawing. I mean, we have defined the product of two combinatorial objects, the sequence, the inverse, so I can really make computing on the set of combinatorial objects, or conversely, taking the part of the calculus and putting them associate some combinatorial objects. So what is the philosophy is, instead of having an equality between in calculus, you replace this symbol by correspondence bijection, and you get a better understanding of the. So bijective combinatorics, example of bijective combinatorics. Again, let's go back to the binary tree. So the Catalan number, we have give a proof in a modern way using symbolic calculus without any recurrence relation, but we have a lot of small computation. We solve a quadratic equation. We expand in power series with the square root of 1 minus 40. So we lose completely we have lost completely the binary tree. So a more bijective proof would be to prove this identity. What does it mean? Cn is the number of a binary tree, and n plus 1. What is n plus 1? It's the number of leaves. So you choose one of the leaves. Now what is the left-hand side? 2n choose n. 2n choose n, you take 2 endpoints, and you choose n points in 2 endpoints. So exercise. It's not easy. Try it yourself this evening. You will see that it's not obvious. To find a bijection between a choice of a subset of n elements over 2n elements and a pointed binary tree, where one of the leaves is pointed. So there is some bijection, but you have and then the interest of doing this is that you are going inside the combinatorics of binary tree. You don't use a powerful analytic computation. So you have more information on the combinatorics of the binary tree, and you will see it's not obvious to find such a bijection. But there is another formula also, which is equivalent to the first one. Instead of 1 over n plus 1, 2n choose n, very small computation show you that this is equivalent to this formula. So you should prove this. Now this is totally different. There is a bijective proof of this, which we will use in a chapter about the Catalan garden. We will use a fundamental lemma, which is called the cyclic lemma. There is a cyclic lemma which proves this identity, and this proof is totally different than the proof of the first one here. It's totally different bijection. So maybe you can say, I am too purist that this identity, if you are not allowed to do anything, then the direct proof of this will be totally different from the first one. So sometimes it's a game, it's a play that for simple identity like this, don't do anything, try to prove directly this. And now the formula for Catalan number, Cn equal 2n choose n divided by n plus 1, this formula is equivalent to this. It's equivalent to this recursive formula, because if you write Cn equal 1 over n plus 1 to n choose n, you take Cn plus 1 divided by Cn, and you get this. You get 2 to n plus 1 divided by n plus 2. So again, you can ask, find a bijective proof of this. So in the chapter on the bijection around Catalan, I will give you the 3 bijection. And this bijection is very interesting to find, because you can get very efficient algorithm to get a random binary tree. How it looks like a random binary tree with 10,000 vertices. So if you choose Cn by random, this one by random, this one by random, apply the bijection, you get a new binary tree by random also. This is maybe the easiest way of the 3 exercise. Maybe try this one before next lecture. Because this is a choice of a tree. 2n plus 1 is a choice of one of the vertex. There is n internal vertex, n plus 1 external vertex. So you choose any vertex in the tree, and you do something in 2 different ways. You are going to increase the number of vertices of the binary tree in 2 different ways. And what you get is a binary tree with 1 more internal vertex, and n plus 2 is going to be the number of leaves, number of external vertices of this one. So if you want to go backward here, you have to point one of the external vertex. So all of what I have said, you should be able to try to find a bijective proof of this. And dig path. A dig path, it's a sequence of vertex on the square lattice. They start at level 0. You can go to the northeast or go to the southeast. Up and down, you stay always above the 0 level. And at the end, you finish at the 0 level. So it's called dig path because Van Dyck was working with 3 groups. there was some word. This is x, and this is x minus 1, x. So this is related to generator in the free groups. This is what is called Dick path, or chemin de Dick path. And so we need Dick path. If you want to find the generating function of Dick path, take the first time you touch the 0 level, and then you can, you can split the Dick path into first a northeast step, then you have a certain portion of the path which is above this level 1, and then you go back to level 0. So you just distinguish the first time you go back to the level 0. You are sure that this will happen because at the end you must go back to level 0. But you cut the Dick path the first time you go to level 0, and what you get is a decomposition. This is a Dick path above the red line. This is another Dick path. So you get this equation. A Dick path can be considered if I take the number of Dick paths of length. The length is even of length 2n. So I take the generating function sigma over an t power n, where an is the number of Dick paths of length 2n. So what you have is a Dick path is an empty Dick path, or maybe it's decomposed into a pair. There is a pair of 2 Dick paths, and t, the variable t, for this down step. And you remember the tree? The tree and the Dick path have exactly the same equation. So the number of Dick paths of length 2n must be exactly the Catalan number. Again, the chapter about bijection, I will give you a bijection, or maybe you can try to find the bijection between Dick path and binary tree. So we have seen, in conclusion of this today, we have seen 3 incarnations of Catalan number, triangulation of a regular polygon by Euler, binary tree in all the story, and now path, Dick path. So this is 3 different interpretations of the same sequence of number, Catalan number. So this is a very beautiful garden, the garden of Catalan. There are many, many different interpretations. So I will select the main interpretation, the main bijection, and this will be useful all along this class and also the class for the following year. Okay, thank you for today, and thank you for listening. That's the end.